Hello, everyone. Sorry for the wait, and I think we're gonna go ahead and get started and kick it off. Thanks so much for all of you coming. I'm reading the chat, and all of you guys are in many places, not just Canada. So this is great. Thanks for coming. Welcome, and hope you can stay for the whole time. We have a whole lineup of speakers and also some trivia for you today. So hopefully you'd enjoy some of it and learn a little bit and take something out or review stuff that you already learned. We'll go ahead and introduce ourselves later on, but first we'd really love to just talk about a little bit of the ground rules. So we have a liaison here from RISE, which is Respectful Inclusive Scientific Events. She's trained in this training, and so we have Audrey who's waving at you if you see her. She's from the GSA, and it's just essentially we would love if we can just make this event respectful and inclusive, and obviously showing some respect and speaking up if there is something that happens, and you can report your concerns to Audrey or to this email as well.
Good morning. And originally the GSA meeting was going to be situated in Montreal, and I just wanted to start this morning to acknowledge that Montreal is seated on unceded territory of the Kanien'kehá:ka. Tiohtià:ke is a place which has long served as a meeting site and exchange among nations, and we wanted to recognize and respect the Kanien'kehá:ka Nation as the traditional custodians of these lands and waters, and today is the home to a diverse population of Indigenous and other peoples. And I have the pleasure of working at McGill University, which is also located in Montreal. And so I just wanted to give us a moment to reflect about the lands where we work and live. And with that, I'd like to introduce myself. I'll be one of your trip leaders today. My name is Kristen Rodziniak, and I am the Outreach Administrator for the Earth and Planetary Sciences Department at McGill University. I also completed my master's here a while back, where I was part of the Canadian Astrobiology Training Program, and also created was participated in the research affiliated program at the Canadian Space Agency. I have the pleasure of being an alumni of the International Space University, and my introduction to space was through the Student Astronaut Program on the Mars Exploration Rovers. And I'm joined today by my friend Chimera, who is my co-field trip leader.
Hi, everybody. So as Kristen said, hi, Dr. Marie-Josée. She just came in and I was like, oh my gosh, she's here. And I just finished my master's at Western University just this summer, focusing on geophysics and planetary science, mostly ice and radar on Mars. And I'm also currently part of the Canadian CubeSat project, which is hosted by the Canadian Space Agency as the ground station lead for Western's CubeSat in conjunction with the Nunavut Arctic College. Ukpik-1 is the name of our CubeSat, and currently I just moved to the Netherlands and to start a young graduate traineeship with the European Space Agency, and so currently it's very, very fun. 2 months, first 2 months of this traineeship, and also the president of SEDS-Canada, which hopefully you learn about more today in our networking session with the representatives from that student organization.
So here's a quick overview of the schedule that we're going to do today. You've now met both Chimera and I. We're going to do a quick icebreaker activity to meet, and then I will have the pleasure of introducing our keynote speaker, Dr. Marie-Josée Potvin, followed by some Canadian space trivia. We will also have some planetary scientists speak to us about the some of the work that's being done at the Canadian Space Agency, and then we will have a breakout room session at the end to introduce some of the opportunities that people can participate in, the Space Generation Advisory Council, Students for the Exploration and Development of SEDS, and the International Space University. Hopefully you can stick around for all of this. And we'll also have a short question and answer session at the end of each of our guest speakers. So thank you very much, and hopefully you enjoy our schedule for today.
And
And
just going over some, oh yeah, sorry. Go
no,
ahead,
go ahead,
Kristen.
Shamir.
And just going over some Zoom etiquette, Kristen had already mentioned that the session will be recorded. And I know we're all excited about space, and so we just advise you to keep your mics off and muted unless asking a question, or you can also type them in the chat and make use of that. And so to start us off, just to get to know our audience a little bit before we introduce our keynote, we'd like you to go to menti.com and welcome you to open the website and type in the code as you see on the screen. So I'll give you around 30 seconds to do that, Wi-Fi speed dependent, but the code is 9178227. And if you have any questions on that, it's going to be a word cloud that we're going to be creating. So you should have some blanks on your screen and fill those blanks in with what the words space exploration mean to you. So I've actually launched the word cloud now, so we can see if anybody has put in any words. So I encourage you to put maybe 2 or 3. And as you see, moon, Mars, awesome. The most frequently typed in word will appear bigger. Exciting, fun, thanks. And you can also put phrases of what space exploration means to you. Lately, especially this week, has been a very exciting week for Canada and sample return missions in general, but I won't spoil anything and let some of our speakers talk about that. But it's really good to hear and see that you guys think moon, curiosity, future of humanity, mostly Mars. People have put Mars as the biggest word most frequently. Okay, next frontier, perfect. Yes, because that's kind of where we are going now with all the Lunar Gateway plans and the Artemis generation. Yes, Mars is still in the front running. But thank you for filling that out. I'll make sure to use this kind of as a metric for our audience members in the room. But without further ado, I would like to give the floor to Kristen to introduce our keynote speaker.
I'm delighted to welcome Dr. Marie-Josée Potvin. She holds a bachelor's in physics engineering from Polytech University, a master's in mechanical engineering from Queen's University, and a PhD in mechanical engineering from McGill University. Her first assignment at the Canadian Space Agency was to train astronauts to use the Canadarm2. Lately, her responsibilities have included training recent graduates in engineering to turn them into seasoned engineers ready to be deployed in all sectors of the Canadian Space Agency, as well as mentoring research groups looking into the use of composite materials for lunar exploration. So thank you very much, Dr. Potvin, for joining us.
Good morning. So it's my pleasure to be here. When we started talking about this initially, you were all supposed to come to CSA, and I would have shown you the hardware everywhere. But I guess we'll have the next best thing, which is like talking about everything we've done and showing you some pictures of it. So I have a presentation. Yes, good. I'll be sharing that. All right, so let's go on our virtual tour of the Canadian Space Agency. So for those who don't know, the Canadian Space Agency is on the South Shore of Montreal. It employs about 700 people, which might seem a lot, but the way it's divided is about a bit over half of those 700 employees are corporate employees, meaning people who will deal with contracts, international agreements, of course, finance, HR, comms. And then a bit less than half of that is engineers, scientists, and technicians. So to most of us technical people, it seems that this is way too little, and we'd like, you know, the technical part to take over more of the agency. But that ratio is a ratio that is found in all space agencies because of the importance we put on collaborating with partners, and therefore you need good agreements and ways to manage those partnerships. So this is a pretty standard ratio. What is the mission of the Canadian Space Agency? It's a federal agency, and its mission is to increase the knowledge we have of space and exploit space for the benefit of all Canadians. So we're really talking here into peaceful, productive use of space. We do this by participating to major projects that are part of the international community. So we participate to the International Space Station, the Radarsat Constellation, James Webb, Gateway. So the big name projects you hear out there, most of the time Canada is part of it. And I will show in this presentation how, as Canadians, we do participate and what are the benefits of this. So one of the big projects that is out there in the international community to which we're participating is James Webb. So many of you attending this conference are probably too young to remember this, but Hubble was our first space telescope. So it was the first time we were launching a telescope in space, and we could actually get images that were not distorted by the atmosphere or other phenomenon. And so we learned tremendously through Hubble. What you have to know, though, is that most of the time a spacecraft can survive the space environment about 7 years. That's sort of a standard. Sometimes for very elaborate piece of equipment, we have a 15-year lifetime, which means we invest in much more carefully crafted parts where we put more aluminum to protect over more radiation and so on. But 7 years is pretty much the standard. Now, Hubble has been in operation for much more than 7 years. And the only reason why it has survived so long is because we used to have the space shuttle that could go up to that altitude. Hubble is at 800 kilometers, and do some repairs. And so we repaired solar panels and mirrors and all sorts of things to improve Hubble. Now, the space shuttle eventually became old, and they we knew we couldn't save them safely anymore for the crew. So then we decided to retire them, and that meant the end of Hubble. We knew now Hubble is still operating, but it's operating as it can. We cannot repair it anymore. And the international community gathered and said, we cannot just stop increasing our knowledge on space, on deep space. We have to put another of these spacecraft out there. And so, of course, if you're going to do another one, well, you might just as well do better and more challenging. So James Webb will be located at a Lagrange point, which is a stable point that we have in different locations due to it's stable compared to the gravity of the sun, the Earth, the moon, and so on. And so the Lagrange point that we're sending James Webb is 1.5 million kilometers away from Earth. So forget about doing repairs. Like if we can only do repairs at 800 kilometers when we have a space shuttle, at 1.5 million kilometers, we're not going to repair anything. So this is extremely challenging. It has to work well on the first time. Now, the way Canada proceeds in those big international projects, they're extremely costly. And there's only 38 million Canadians or so we can only pay so much. So the way Canada proceeds is that it enters partnership and say, okay, we're going to provide some parts, but in exchange, we want some data for our scientists. And so the money we invest in those parts creates a very high qualified job and expertise in Canada, but also provides access to data to our scientists. And this is what we did for James Webb. So we said we're going to provide two instruments, the fine guiding pointing system and the spectrometer. And those are key instruments. And they've been built in Canada, tested, and they're already in James Webb being integrated. And in exchange, Canadian scientists are going to get 3% of the imaging time. So that's how you sort of negotiate this. So James Webb is integrated, has been going through some final testing. Last I heard is what it was due to be launched in 2021. I don't know if the pandemic has slowed that schedule or if things have happened, but that was the last I had heard of it. Another big projects that Canada actually led is the Radarsat suite of satellites. So Radarsat 1 was launched in 1995, so quite a while ago, and it lived 15 years. And again, it was like meant to live 7 years. So if we look at the, this is Radarsat 1 here, and I don't know how I ended up with a funny pen like this, but anyway, so this is, here we see the radar underneath the satellite. That's the imaging part. It's a radar, therefore it sends electromagnetic rays on Earth, which bounce back, comes back to the instrument here and are decoded and the image is formed. And this plate has to be very stable to be able to compare the data received at one end to the other end. and it's 2 meters about approximately by 15 meters. So it's a huge, huge instrument. And when Radarsat was launched, it was one of the few could do that, and it provided invaluable images in terms of Earth observation. So these images were used to monitor floods, ice melting, oil spills, changes like deforestation, changes in the Earth structure, Earth pattern. And so it proved very, very useful. Now, what you have to know is that building a satellite and launching it is no minor thing. It takes about 15 years between the time like the idea emerged and someone says we need that satellite, and then you need to do a few studies and build a proposal, which is no trivial thing. Build a proposal for Treasury Board and argue with it, and then once you get the money, then you need to get the contracts out, get the teams prepared, and then start conceiving. And then once you have a concept, then you need to test that concept, calculate, and go into further design. Eventually, you start manufacturing the parts, testing them, and then finally launching them. And that takes about 15 years. So pretty much as soon as Radarsat was launched, Canada started thinking about the successor of it, because they knew this satellite was meant to survive 7 years, and we would need another one after that. So Radarsat 2 was designed, and we see it here. It's about the same size, but the same concept. It has a bit more possibilities than Radarsat 1. And Radarsat 2 was launched in 2007. So you can see there we were way past the 7 years mark. Why did the Radarsat 1 was conceived for 7 years and lived 15 years? 7 years is a question of probability. You know, you're getting hit by a normal rate of radiation and so on, but you can be lucky and never get a debris hitting you, never get a meteorite, which of course would be a bit dramatic, and never get solar rays that would be too damaging. So Radarsat 2 was launched in 2007, is still in operation, and is still extremely useful. But even a bit before the launch of Radarsat 2, people start sitting down at CSA and say, okay, what will be the next thing? Because we know there will be a next thing. Radarsat 2 will probably live 7 years. And that's when we started designing the Radarsat constellation. So we went for something a bit different. So Radarsat 1 and 2 are both at about 800 kilometers. And so, which means that, you know, they go over the Earth and the Earth rotates underneath, and Radarsat 1 and 2 will get to the same spot within about 4 or 5 days in most cases. And there were instances when this was a bit problematic. For example, there was a French sailor that capsized in his boat in the South Indian Sea, and France asked us to try to locate the sailor, and I can't remember if it was Radarsat 1 or 2 got an image of something that seemed like a sailboat, and so they had sort of an idea where the sailor might be, but then the satellite would only get over that area 5 days later, and of course when it came back 5 days later, we couldn't see the sailboat anymore. So for reasons like this, there was an interest in having images that could be done every day, like having be over each spot, being able to go over that spot every day, so you can get some images. And so that's why we went for a constellation. Rather than have it at 800 kilometers of altitude, we lowered it down to 600 kilometers, which means that each satellite is spinning faster around the Earth and does more rotation around the Earth in one day than if it were at 800 kilometers. Moreover, there's 3 of them in the same orbit, so they're 120 degrees compared to each other. And so when one goes, like a few minutes, hours later, you'll have the second one coming. Well, a few minutes later, you'll have the second one coming, and so on, which means that certain locations in Canada will be viewed several times per day, but at least every location will be seen once a day. And so we started work on this around 2005 or so, and it was launched in 2019. So it does give you the time span it takes to launch these massive programs. Oh, and they're a bit smaller than Radarsat 1 and 2. The plate you see here beneath is about 3 meters, so it makes them a bit more manageable. We're working on an International Space Station, which is orbiting the Earth, and And well, it's huge. It's several hockey rinks together. And here you see a little arm sticking out, and that's the Canadarm. That's the contribution Canada has done to the International Space Station. Now, it seems small, but it's 17 meters long, so it's not that small, and it's extremely important. So here you see like a close-up view of the arm, so you see it has like 4 sections because it was so huge it couldn't fit into, as it couldn't fit into the space shuttle. It had to be folded in pieces. And it's entirely symmetric. And here you see, so you see the extremity of the arm. Here it has a cavity, and that cavity is designed to catch those grapple pins. So you see them here. They're about 30, 40 centimeters high, and that's what the arm can station. And what the arm does is that it goes and grasps a pin, and then will release the other end, and just goes just like a worm a bit, and then goes to the next grapple pin, and so on, and move from grapple pin to grapple pin. So the Canadarm was a departure in the way Canada had proceeded before. With the space shuttle, Canada had provided some arms, but it had like built the arm and then given them to NASA, and NASA was to operate them, train the astronauts, repair them if there were any issues. With the Canadarm 2, Canada said, we're going to keep responsibility for the arm. We're going to train people, we're going to repair it if it needs to be repaired. So it built more in Canada, but also proved to be, and over time it proved to be much more than a building block. It also became the only way to catch free flyers. So it wasn't meant at the beginning to be, the space station was meant to be serviced with Soyuz and the space shuttle, but over time, the variety of vehicles that came to the space station increased, and some of them needed to be caught as they were flying by the space station, and the arm did this. And it wasn't designed for that initially, but we sort of adapted, and it was able to do it. It also has been used quite extensively for inspection of the space station. We realized that there's quite a few debris out there, and their number is increasing every year. And from time to time, you hear a little bump, and something is bumped into the space station. And the Canadarm is used to inspect the space station and make sure that everything is good and everyone will be safe. So of course, another thing we do is astronaut training. So here you see Jenny Side, one of our latest new members in the astronaut team, training on the Canadarm. And this station we have, apart from the fact that she's sitting on a chair, is the station we have that is the most representative of what they have in the space station. So you can see here she has a laptop, and on that laptop she would have the position of each joints of the Canadarm, ensuring that she doesn't overreach, ensuring also that she doesn't reach a singularity. So like the way we control arms in robotics is that we'll have a matrix representing the motion, and then you have to invert that matrix to find if you guide the endpoint, what will be the motion of each. For example, when everything is extended and all the joints are at 0, that's one singularity, because then the software would know, well, if I have to move a bit, do I move this joint? Do I move this joint? Do I move this joint? And it has too many possibilities, and then it just jams. So she has to watch, she has to keep an eye on that. There's not that much intelligence into the system, because you have to remember that the same way it takes 15 years to build a satellite, it also takes a long time to build a Canadarm. And the Canadarm was launched in 2001, but the construction planning of it started in the 1980s and early 1990s. So the technology that is on board is a technology that was used at that time, and artificial intelligence was not around yet. So a lot of it is the astronauts must do manually. Now, I often get asked, why don't they just upgrade the systems? It's pretty complex. You have like this whole integrated system. For example, on the arm, we'll go back. On the arm, you see those big boxes here. And here, it's a bit tough to see this one. They're actually the computers directing the joints. And each joint has a computer. It was decided to have a distributed architecture architecture. And they used for it what the most powerful computers they had at the time, if you think middle 1980s or so. So all the computers, you know, like directing the joints are 8086 and 386. So that's when you had a DOS environment, and you would actually program by counting your number of characters, making sure your lines were as short as possible, that your variable names were as short as possible, that that you emptied your memory after every task, and so on. So that's the kind of, it's still programmed in Fortran. So when we hire new young engineers to work on the ARM, they have to learn this, because we cannot upgrade 8086 and 386 to do more complex tasks. This is the memory they have. And now we couldn't go on the ARM and start changing the computers, because that would change the mass distribution, the thermal distribution, the power needs, and then the whole ARM would be wouldn't be functional anymore. So we live with the technology we have, and that means that the engineers have to, well, the astronauts have to be very careful about the position the ARM is, make sure that the joints are not overreaching, and they have to keep the speed of the extremity of the ARM extremely low to avoid getting into vibration and losing control of the ARM. You can see the two hand controllers here. So on one side, this one is to control the translation, X, Y, and Z. And this one controls the rotations around each axis. So you have to learn to play with both hands, doing two different things. If you've played a lot of video games, it's much easier than if you haven't. But I mean, eventually everyone gets to train on it. And then there are these three video screens here that you see. We now have a cupola in the International Space Station where astronauts can look through, but not all operations are necessarily in the vicinity of the cupola. And so before they have the cupola, or if they're not in the vicinity of the cupola, they have to rely on video images to see how they operate. So they will always keep an image of the target they're trying to catch, the grapple pin, to see if they're well centered, if they're approaching well. And then they'll have another image, which will be the lateral view between the extremity of the arm and the grapple pin, to make sure you're close. Because if you're having this view and you're approaching, you're not too sure about your distance. Whereas on the side view, then you can see how close you are. And the last view is the elbow, because it's a 7 degree of freedom arm, just like yours. It has 3 ways to move the wrist, 1 way to move the elbow, and 3 ways to move the shoulder. And because of that, because it has 7 degrees of freedom, whereas you have only 6 coordinates, the 3 translation and the 3 rotations, you have more than 1 way of doing a given thing. And for that reason, the arm could, it's the software that will decide which joint will be moved to get to where you want to go. And there's more than 1 way of doing it. And the goal, while your goal might be to make it as simple as you can, and you sort of, I'm here and I'm just going there, and that's pretty simple. The software will want to minimize the wear and tear on always the same joint, namely the elbow. You know, they will want to avoid the arm getting a tennis elbow, like doing always the same motion. So it will, if you want to go there in your head, that seems pretty simple, but actually what the arm will do is probably a shoulder motion and a wrist motion and some elbow motion, but not that much, and get to the same spot with the same orientation. But you have this big 17-meter structure that will move and can actually hit something and kill everyone on board as they go. So that's why astronauts will always keep an eye on the elbow. And that's extremely demanding. It's a lot of facts to take in and control and make sure that everything goes fine. And as years evolved, the astronauts realized this was pretty tiring. Missions can go for 5, 6, 7 hours where you have to be at maximum attention. You don't have the benefit of a chair. You don't feel gravity. So even if you had a chair, you would sort of be hovering around it. So you're sort of, every time you move the hand controllers, you're moving them against your whole weight, which is much more draining than on Earth when you benefit of the friction of you sitting on the couch. So all this to say, it was very tiring for the astronauts. So over time, ground control started taking over many of the operations, to the point that they're now doing 90% of the operations. They do them mostly when the astronauts are sleeping. That way there's no vibration into the International Space Station, and it makes it easier for them to just go around and maneuver the arm. Okay, and so the next natural step after the International Space Station was to say, well, we will participate in Gateway. So Gateway is the space station that is planned to orbit near the Earth, the moon. It will be, again, a bit like James Webb. It will be orbiting around the Lagrange point because the moon doesn't have a very stable gravity field. It changes from place to place, so it's tough to have a stable orbit around the moon. So by being around a Lagrange point, then you'll have the moon and you'll have the spacecraft orbiting near the moon. And so it will always have some view on the moon and some view of the Earth. We'll be able to communicate with the Earth while monitoring what's going on the moon. This was an early design. It might have evolved since I got that picture, but what I want you to notice is that there is an arm on it, you know, and it looks pretty much like the Canadarm2. And that's because international partners realized that the arm had been an essential part of the International Space Station, and you couldn't actually envision building another space station without putting an arm on it. So Canadarm3, very originally, that's how it's going to be called, is going to be the arm on the Canadian, on the Gateway, on the space station orbiting the moon. It's going to be similar. It's still like being finalized. We're still in phase 0, so designing the arm and the concept of it, but it's going to be very similar to Canadarm2. It's going to have a smaller arm that it can use at the extremity to do finer tasks. But you can sort of see the same concept here that it's going to be used. They're still finalizing the kind of materials they're going to use compared to what they used for Canadarm2. Well, there's concerns that we didn't have for the Canadarm2 that we have for Gateway. The Gateway space station is not going to be crewed at all time. There'll be, because of the high level of radiation and the fact that we're away from the magnetosphere, means that the astronauts are left with little protection. And for that reason, they're going to come for short stays and then come back on Earth. And most of the time, the Gateway is going to be uncrewed. So you need the arm to be able to perform all the maintenance tasks that normally a crew would perform. And you need some automation in there because there's a delay in communication between where a Gateway will be and Earth. And so you need more autonomy to be built on this. This is going to be done baby steps. You don't want to start having an autonomous system, which you can't test on Earth, which is a big thing. The arm, the motors that you can see here can sustain the weight of the arm in space when the only thing they're sustaining is the inertia and not the whole mass because they're not feeling gravity. But it cannot be operated on Earth. It wouldn't support its mass on Earth. Now, even if you put it in a pool where you sort of upset gravity, then you still have like all the friction caused by the mass of the water around it. And so the motors will not be powerful enough. So the arm cannot be fully tested on Earth. So when you launch it, you're sort of learning as you go how it reacts. And that means that we cannot design elaborated AI scheme that will sort of learn the motion of the arm. We sort of have to learn as we go, and so it will be given autonomy very slowly as we understand its behavior and make sure that everything is done safely. The other thing is that we're also more concerned about radiation, so we have to protect more of the electronics. We have to worry about the material we're using. We use PEEK, which is a thermoplastic for the Canadarm2. PEEK is very resilient, but we still have to evaluate in a high radiation environment how it would behave. So I think that's the end of my story on the space. Yes, it is. So this was a very brief tour of the Canadian Space Agency, and I'll be happy to take questions.
Thank you so much for such a comprehensive overview of the CSA's current activities. We would actually encourage everybody, if you would like to ask a question, to even unmute yourself and also turn on your camera so we can hear your questions. Or if you'd like, just type it in the chat as well. We have a few minutes for questions before we can go to the next trivia fun part for the Canadian space sector in general, and some fun facts that you may or may not know already, maybe about astronaut training or the Canadarm. Yes, please ask questions. We are so lucky to have Dr. Marie-Josée here today. So thank you so much for coming.
It was my pleasure.
And we hope in future we'll be able to come and actually visit the space agency and get a tour. So I think that's something that's really special with the Canadian Space Agency, is that they do offer public tours. So that's wonderful. Well, obviously not during COVID times, but I think that's something that's very special with our space agency.
After that. And I just want to precise there, we're not exactly offering public tours. We're offering tours to specific groups who have a goal. And so this is, yeah, I'm always pleased to do it, but it's not as simple as saying I want a tour and we get it. You know, there's a question of availability and the purpose of the group and so on. But we've had your group in the past, and we'd be happy to have you again to the Canadian Space Agency. I saw a question in the chat. Maybe someone wants to read it to me.
It's so from Purich Moonlow. We have, what are ongoing projects that are happening at the Canadian Space Agency at the moment?
A lot of what I've talked is ongoing because, for example, the Radarsat Constellation, even though it's launched, we still need to operate it, and so there's a lot of people working on the operations of Radarsat constellations, making sure we get the data, we prepare the data, distribute the data, and so on. Then there's the International Space Station is still operating, so there's a lot of people working on that, preparing missions. Every time the Canadarm is used, it means Canadian operators prepare the mission, oversee the mission, and so on. So there's a huge sector dedicated to that. Of course, there's a lot of people working on Gateway, preparing the next project. James Webb, there's still people stand by in the sense that the Canadians have done their instruments, but they're being integrated. And as testing goes on the whole integrated satellites, there's always risk that something happens. So the team is sort of standby, ready to help if some issues happen with the two Canadian instruments. And then we have some other smaller missions that are in the play. So everyone is actually very, very busy. It was quite something for us to discover that COVID didn't change anything in our workload. If anything, it increased. And engineers have been stepping up. You know, we've all been working extremely hard and delivering despite the constraints that this new environment brings to us.
Awesome. We have another question from Kutan Salabi. How can researchers help better formulate experiments and questions to help Canada's future in space? And then there's a second part to that, but I can ask you that after.
Okay, good. Well, it's that's quite a good one. You know, the scientists have to learn to think into telling the story of their science experiments. I often review proposals from young scientists, and often they're really, really intense into their data and what they're going to get and how cool that is, but they cannot tell you the story about why this is important. And I think that's something that we learn over our careers. I'm a researcher myself. You learn to tell the story, not just the cool equation and the cool data set, but the story that goes behind it. Why is this useful? Why does this matter to Canadians? It matters to Canadians now, but what will bring as a difference for Canadians in 5 years, and 10 years, and 25 years? And is it just for your little sector? What impact will it have on the broader sector? So learning to tell the story is one big thing. And when I review grant proposals from young researchers I'm mentoring, I'm always go, where's your story? Tell a story, you know? So I think that's, if you want more grants, more money, convincing more people, you have to learn to tell the story.
Okay, awesome. The next question is just about funding and what areas need more funding focus in your opinion. If you'd like to answer that briefly, and then we can go to one more last question.
Everything needs more funding. Every research sector will tell you they need more money. It's an exercise in prioritization. What is the most useful thing for Canadians at this point? I think climate change is one big thing on the agenda. So all sorts of data sets that help us understand climate change and do better with it is a huge priority for government. Of course, security in our sort of environment right now is a big priority. So if you look at the throne, the disclosed throne, I'm forgetting the word in English, but if you the speech of the throne, if you look at the speech of the throne every year, it will tell you the priorities the Canadian government have, and these are where they will try to put money. So that's also a good thing to do as a researcher, is to read the speech of the throne and say, okay, this is the priority of government. How do I insert myself into this to learn to be relevant to the Canadian government?
Okay, awesome. Actually, let's take a few more, two more. And one is asking about the resolution of Radarsat. If you would care to explain about the resolution, and also are those small satellites, which I think we explained in the talk.
Okay, so for the resolution of, well, the resolution doesn't quite depend on the size of the satellite as much as on the type of instruments you have on board. So if we think about, I don't have the exact numbers, but it's a few meters. So we're actually, Radarsat 2 and the Constellation have actually are very precise satellites, seeing objects that are a few meters long, wide, or whatever. So it's a very high resolution. So there's many things to the efficiency of an instrument, its resolution, how large an object it can pick, but also how often it revisits, and the shades of intensity it can detect to tell you, you know, is this metal, or is this, is this a humidity? So there's several aspects to the precision of an instrument. And when you design a mission, the first question you ask is, what do I want to see and why? And that tells you the kind of intensity you need, the kind of the size of objects you need, the time of visit you need, and you design the instruments according to this. And that's true for big satellites as Radarsat, but smaller ones also.
Okay, I think we'll take a last question just about the timeline for the Canadarm3 and Gateway. I know you mentioned that it's still in phase 0. Oh, sorry.
I know, but it's moving fast. It's within a few years. You know, they want to be on the moon within a few years, and then they want to have Gateway a few years later. So it's moving at a very, very fast pace. We'll see if the schedule that is out there is sustainable. Of course, as you build those huge projects, you have a schedule. It's always the first thing you're building. So it's not like if you're building toasters, after a while, you're pretty good at building toasters, and you know that it's going to take so much time to build a toaster. Whereas these satellites, it's always a first, one of a kind. It's always the first time we're building this. So we build schedules, and they regularly slip because we encounter things we had not planned. But the schedule for the Gateway is extremely aggressive, and it's all coming into the next few years.
Awesome. Okay, thank you so much, Dr. Marie-Josée Potvin. We're going to move on now to our trivia, but we'd love to have you stay if you'd like. We're going to be playing trivia and then also having a few more CSA speakers come.
And just while you're setting that up, Chimera, if Dr. Potvin has time for one more question. There was a question about opportunities at the Canadian Space Agency for non-Canadian citizens. I don't know if you can touch a bit on that.
That's a tough one. Yeah, I can certainly, because I'm responsible for hiring the young engineers. Yeah. So we have to give priority to Canadians, and we can only hire non-citizens if we can prove that there's no Canadian citizens that can do the work. So sometime in a very, very specialized area, we've been able to hire permanent residents, for example. But in most cases, we will find a Canadian researcher that can do the work. So I strongly, anyone who's interested in staying in Canada, I strongly encourage you to get your residency as early as possible, and then your citizenship as early as possible, because it is difficult to hire you without the Canadian citizenship.
Awesome.
Wonderful. There are also opportunities for kind of funding through the Canadian Space Agency from researchers and stuff. So I know that in the past there's been some opportunities if researchers are students at Canadian universities. There may be some funding opportunities that way.
Okay, I'm just going to share my screen. Can you see the screen? Awesome. Yeah.
Thank
Cool.
you so much, Dr. Potvin.
Yes, thank you so much. I'm clapping, round of applause. I'm sure everybody is as well. For our trivia, just to test your Canadian knowledge, I would encourage everybody to try it out. We'd love for you to go to kahoot.it because very, very educational and a good tool to use for big conferences like this. And if you can put in the game pin 4361715, which I think is also going to be in the chat, please go ahead and type in and I'll see you there. We have prepared around 30 questions to test your Canadian space knowledge and just general space knowledge as well. So if we go, we already have Thomas, Audrey, welcome. Oh, you also don't have, if you don't feel comfortable putting your real name, you can also put an alias or initials, that's completely fine. I will wait for a few more, maybe seconds, just so we can try speeding it up before our next speakers come in. Awesome, okay, let's see. Anybody else joining? A few more seconds. If not, you can feel free to just watch along. That's completely okay as well. The questions are all free for everybody to watch. Okay, we're gonna start. Please stop me if, okay, I see AM, thank you. Please stop me if you are still in the process. I'm gonna press the button now, ish. Okay, cool. I will start now, if that's okay. So we start with our trivia for Canada in space with the first question being, which place did Canada come in during the space race? And you're able to click as fast as you can. I think that's how they measure the winners sort of for this. So is it first, second, third, fourth? And on your screen, you can pick which one. So maybe not on the Zoom page, but cool. We came in third place in the space race. It was first the Soviet Union and also the US and then also us.
Shamir, can you share your screen so that we can also see the questions?
Oh, am I not sharing my screen now?
Yeah, but it just has the launch page, not the actual questions.
Oh, okay. Sorry, I must have done something. Okay, 1 second. Sorry, we will pause the game. 1 second. Sorry about that. I didn't realize that it was not being shared. Okay, cool. So it's not, the word cloud is not appearing on your screen? No.
Yeah, we can see the word cloud now.
Okay, and then the Kahoot also is appearing on your screen?
Now we see the questions, that's great.
Okay, awesome, thank you. I don't know what button I hit to not screen share, but now we can see the questions. That's why I was wondering why there was no one answering the first question, because you couldn't see the option and the question. But we'll count the first 2 rounds as practice. Cool. And so the next question, which country first landed humans on the moon? This is actually a trick question. All right, I think everybody has put their answers in. We have 8. So you are correct if you said the US, also Canada. Just because technically the lunar lander's feet and the modules both, or sorry, for how many lunar lander module kind of base foot are there, that's actually made by Canadians. What is the scientific study of the moon called? Cool. Awesome. Yes, the study of the moon is called selenogy. I think most everybody got that. What is the name of the largest visible crater on the moon? I should put on some background music to make it more fun. Oh, wait. I think this might be actually incorrect because the South Pole Aitken Basin is in the... Oh, yeah, maybe we'll count this question as false. What is the name of the largest known crater on Earth? We've got lots of craters on Earth. Yes, it's the Radarsat Formation or crater in South Africa. We even have a map of Canada here to show you how many impact craters. If you can count really, really fast, maybe you get it. "32. Oh, awesome. Everybody got that. Most people got that. Geo, you're winning. Good job. Which was the first fast food delivered to space? This was a fun fact that I really wanted to know and needed to know.
And pictured is one of the Canadian astronauts, Chris Hadfield.
I think this is for the Tomato Sphere project, which, yeah. So Pizza Hut, apparently, is the biggest one. Oh, sorry, the first fast food delivered to space. Could you imagine? Pizza in space, delivered. Who was the first Canadian astronaut to visit the International Space Station? Yes, Chris Hadfield. Julie Payette actually went to space, but not the space station, I believe. Kristen, correct me if I'm wrong, or anybody else from CSA. Who was the first Canadian astronaut in outer space? So not the space station, but just outer space. Yes, congratulations to everybody who clicked mark no. Geo actually is winning up by a lot, but thanks. Okay, who was the first Canadian woman astronaut? We only have 3 so far, so pick wisely. She's also pictured here in this image. It was Roberta Bondar, and now you will never forget who was the first Canadian astronaut, the woman who was in space, Roberta Bondar. Which Canadian astronaut holds the record for the longest spacewalk? For 17 hours and 43 minutes in total. It was, oh, whoops. I'm not sure what happened. There. Dave Williams actually holds the record for the longest spacewalk. Although Chris Hadfield has been in the International Space Station for a while and has a pretty big record for lots of things. But not the longest spacewalk for Canada. This one is sort of easy. Which Canadian astronaut is also the Governor General of Canada currently? Yes, Julie Payette. When was the Canadian Space Agency founded? If you put 1989, you are correct. Okay, we're almost there. Which province is the Canadian Space Agency headquartered in? So this everyone should know because we just listened to a keynote talk about it and mentioned it a few times, some clues. Is it in Ontario, Quebec, British Columbia, or Alberta? Perfect, Quebec. In Saint-Hubert, Quebec. Alrighty, what does the Canadarm do after that in-depth description of the Canadarm 1, Canadarm 2, and now Canadarm 3? Yes, oh, clean sweep. Great job, everybody. Okay, we got a few more. What Canadian-built instrument is on the Mars Curiosity rover? I think these questions are getting a little bit harder now. So these are truly fun facts. All of these, by the way, are payloads on the Mars Curiosity rover. So you can just guess and pick one and see which one works out. Or if you really know, then you really know. Awesome, everybody sort of got that. It's the X-ray spectrometer in Gale Crater and Curiosity, responsible for a lot of the results from mineralogy. Okay, what is the main rock type on the moon? Is it anorthosite, granite, basalt, or diorite? All the geologists would really appreciate this rock type on the moon, I believe.
If you do visit Montreal, there is a, in front of the CIBC on Sherbrooke Street, there's a giant slab of anorthosite that makes the welcome marker there.
But it's not from the moon, is it?
It is not.
Where is this image taken? So we have an option for moon, Mars, Earth, or other of this picture that you see on your screen, or on my screen that I'm sharing. Good, it's actually taken on an asteroid called Bennu, which is a superstar this week, which I'm sure other CSA speakers will talk about and touch on. Another one, where is this image taken of a beautiful colored crater? The colors are not real, they're just multispectral images and some combinations of bands and filters. But those are certain minerals that show those reflectance. So perfect, that's actually a high-rise image of Saheki crater on Mars. I think this is the last one and might be the hardest one because it's just a digital elevation model of a hillshade and it's a volcano. That's all we can say. So your best guess. It's actually in Hawaii. Perfect. That's one of the volcanoes in the islands in Hawaii. How long is a lunar day? Okay, we're pushing through these almost. I agree. Cahoots has a biased design by color. Oh, whoops. I don't know why it keeps switching my screen. I'm so sorry, but yes, 24 hours and 50 minutes. That's kind of an even split. It's actually almost like an Earth day, which is why we simulate lunar analog missions here on Earth, which we actually did last year at Western University and as well as Winnipeg University. And we simulated lunar nights and lunar days and had to wake up very early for this analog mission. What is the name of the first Canadian satellite? You can see it here on this picture as well. Perfect, Alouette 1. What is Canada's contribution to the James Webb Telescope, which was focused on and touched on a little bit? And like before, all of these are actual payloads on the James Webb. So if you know, then perfect. And you definitely, oh no, I'm sorry. Again, my computer screen just keeps changing every time I click something on Zoom. Okay, awesome. Is it? Yes, it's the FGS, but I think not everybody got that. And one of the last questions, who is the first geologist on the moon? We need more geologists on the moon. Even splits. It's actually Jack Schmidt, who was the first geologist ever to go on the moon. Where do astronauts train to use the Canadarm? I'm trying not to give away any hints. Yes, the Canadian Space Agency. It's kind of uniform throughout. Which type of gas was recently discovered on Venus? Exciting news. Life on the clouds of Venus, just like how Carl Sagan predicted. I feel like this would be an even split too. Oh, perfect, uniform, almost. This one is one of our last ones, and it's a tribute to one of the missions that just happened this week. Very exciting, looking forward to all the pretty pictures and results, but Osiris-Rex is the first ever asteroid sample return mission in the world to asteroid Bennu. Is it true or is it false? It's actually false. I also had the same mistake, but it's true for Canada because it's the first time Canada has ever been involved in an asteroid sample return mission. The first one was Hayabusa by JAXA. And it's scheduled to return a sample in 2020 of December, this year. What was the name of the Osiris-Rex sample site that was just sampled this Tuesday, 3 days ago? Successfully. And these, oh, perfect. Everybody already knew. Nightingale. And I love the naming scheme. Maybe Tim can tell us more about that, of just the birds. And last question, what did Canada contribute to the Zyrus-Rex sample return mission? Oh, see, first asteroid sample return, second, which is a typo. I hope you all enjoyed some fun facts and learned something. For this last question, it's the OLA. Osiris-Rex laser altimeter, which is in charge of all the fine resolution elevation images that we get from it. So congratulations to Thomas and Casey. And last but not the least, we also got SK. So perfect. I'm now going to stop this Kahoot and move forward with our presentations and our presenters. So we've got them in the room right now, and I'll pass it on to Kristen.
So our next session is going to be on planetary science initiatives, and I am very pleased to welcome Dr. Caroline Emmanuelle Morissette. After completing a PhD at the University of British Columbia, focusing on iron and titanium deposits related to the Proterozoic Anorthosite Massif, Dr. Morissette had the chance to carry out her postdoc at the Canadian Space Agency, where she studied the composition of lunar ilmenite from Apollo samples. Following this, she worked as a consulting in mining geochemistry with Golder Associates and has recently been appointed as the program scientist at the Canadian Space Agency, mainly working on scientific aspects of the CSA's lunar program.
And I'd also like to introduce Dr. Tim Haltigin, who is another speaker, which he'll talk about more about Osiris-Rex because he is a senior mission scientist in planetary exploration at the Canadian Space Agency. In this role, he helps lead Canada's efforts in finding new ways to explore planetary bodies throughout the solar system. And he received his PhD from McGill University, where his research revealed similarities in the evolution of ice-rich terrains on Earth and Mars. In 2016, he was in the running to become Canada's next astronaut. And in 2017, he had an asteroid named after him. Awesome. 130066, Tim Haltigin. Tim currently serves as the Canadian mission manager for Osiris-Rex, a mission that will return a sample from asteroid Bennu to Earth in 2023. So I'll give the floor to you, Tim and Caroline, and stop sharing my screen.
Perfect. Thanks, everyone. Can you hear me okay? Ooh. Sorry, can you hear me all right?
Yes, you're good.
Excellent. Good. So first things first, thank you so much for having me today. I'm just going to try to get my charts up here, and hopefully it's going to work. If you could just let me know if and when you see it, please.
Yeah, we can see it. Thanks.
Got it. Okay, perfect. So yeah, first things first, thank you so much for having me here to share some excitement about the planetary science program at CSA. So thanks to the organizers for putting this all together. Thanks to you for listening. And yeah, as was mentioned, it's been an awfully exciting week in space, and specifically for the Osiris-Rex mission. So you can imagine there's been a lot of late nights and early mornings. It's been really quite something. So what I want to do today is really just give you some of the highlights. I mean, if we were to talk about the entire planetary exploration program at CSA, we would be here for several hours. And frankly, you know, two of my favorite things are planetary science and wine, and I don't want to keep you from the second part of that. So we're going to sort of run through, we want to leave some time for questions at the end if there's any. And I just want to highlight, I'll be giving the presentation, but Caroline is here as well, and I just want to acknowledge all the contributions. She came on board at the CSA earlier this year and has been utterly fantastic, and we're really, really grateful to have her. So with that, you know, when you think about planetary exploration in general and planetary science, what are we talking about? And fundamentally, you can sort of break it down into two basic questions. One is, you know, what is the solar system made of and how does it change over time? And the second is, what are the limits to life, and is there life somewhere else in the solar system? And obviously, as this is a, you know, an audience focused on geoscience, I think we'll focus more on the first bits. But really, you know, when you think about planetary exploration in general, all the missions we do, they all have different specific objectives, but really they're both trying to answer some of these higher level questions. So when you think about what Canada is then doing to participate in some of these missions, you can sort of break it down into four different categories. One is science instruments. So there's been a variety of flight missions that Canada has participated in, where we've contributed an instrument built in Canada along with a science team to go with it to help contribute to the data that's collected to the mission and the investigations that are taking place. In some places, we've simply provided some technology. So I think during the quiz, we'd mentioned that there were Canadian feet on the lunar lander. So there's other satellites and there's other spacecraft out there right now that have Canadian technologies on them as well. Third is science team participation. So sometimes there's Canadian scientists across the country that are so good that they've been invited to join the teams of international missions, and we help support their participation on that. And finally, there's a lot of work in terms of preparing for the next step because of the amount of time it takes to get a flight program approved and funded and designed and built and tested and launched and finally into operations. You can't wait until one is done to start new ones. So there's always a lot of development work going on as well. So I want to touch on some of the highlights of each of these four again, just to give you sort of a basic overview of some of the things we've done in Canada in space. Now, because Canada's program obviously is a little bit, well, it's substantially smaller than NASA's, for example, smaller than ESA's, we have to be pretty selective about what targets we pick and what we focus on, because the reality is just we can't do everything. And so traditionally, when you think about the Canadian Planetary Science Program, it's been primarily focused on 3 targets in the solar system, the Moon, Mars, and small bodies or asteroids. And so we currently have missions either in flight or in development for each of these. And it's a pretty neat time. So obviously, I would love to have a $10 billion budget. I don't. And so what we do is we work with the budgets we have and really try to make the biggest impact we can for, to meet the resources that we have. And I think, to be perfectly frank, Canada's recognized for punching above its weight and doing a great job with what we have. So in terms of this first category, what are some of the science instruments we've flown in the past? So the first one, what is known as the MET station, or the meteorological station, that flew aboard the Phoenix Mars lander back in 2007. So this was a mission that was led by NASA that landed actually very close to the North Pole. And the goal of this mission was to understand the water cycle on Mars a little bit better. So Mars right now is bone dry at the surface. There's liquid water can't exist because the atmospheric pressure is too low. But there was thought that there's lots and lots of ice right underneath the surface that's protected and sort of shielded and can stay solid. And so this was a mission really trying to understand, A, is there ice in the surface? And B, what's happening in the atmosphere and what's the exchange between the subsurface and the atmosphere? And so they landed close to the North Pole at a site that they believed they could find subsurface ice, which they did. Now, the Canadian contribution, you can see sort of the green laser. This is an artistic impression, but we had the MET station, which consisted of a number of instruments, but the sort of star of the show was an atmospheric Lidar. So this was an instrument that was used to shoot a laser out into the atmosphere that would bounce off of small particles in the atmosphere and come down. And based on the difference, based on the time it took for a laser pulse to come out, bounce off of something, and come back, you can measure a distance to what that reflector was. And so basically, by shooting all the way through the atmosphere, you could get a profile vertically through the atmosphere of the particulates and differentiate between dust and ice and things like that. And what's really neat, so this was the mission that sort of metaphorically planted the maple leaf on Mars for the first time. So this was our first attempt at a planetary instrument. But what was really neat are some of the results that came back. And so when I talked about this vertical profiling through the atmosphere, what it showed is these fall streaks that you can see on the left side of the chart. That's actually ice particles that are starting to descend. So this is precipitation. And ultimately what that means, frozen water ice precipitation is snow. And so this was the first time that snow had ever been detected in the Martian atmosphere. And so the joke we always use is that it's only appropriate that if anyone was going to find snow on another planet, it should be the Canadians. So we lived up to our, roles there, and it was a tremendous success with a science team led by York University. So next we have the APXS, or Alpha Particle X-ray Spectrometer. Again, this is one that was sort of introduced during the quiz in the break here. And so the APXS is the instrument that you can see right in the middle of your screen, sort of the rectangle with the circle in the middle of it. We call it sort of a radioactive Coke can that's out on the end of the arm of the Curiosity rover of the Mars Science Laboratory, which is a NASA-led mission. So MSL landed inside a crater on Mars called Gale Crater, which is near the equator. And this is a really neat place because a lot of the indications that we had about Gale Crater, just from orbital measurements, was that this is a location that likely used to have liquid water. And so the mission, the objectives of this mission was basically to go down and to interrogate the rocks that are there now, to try to reconstruct Martian history, to understand if this location was potentially habitable several billion years ago. And obviously, as you know, a group of geochemists, you understand that rocks preserve that history. They tell that story. And so by going out and doing spectroscopy on these rocks and understanding the chemical makeup, what you could do is basically go back in time by 3 billion years to when these rocks formed to understand the environment in which they were formed. So that's exactly where APXS comes in. So this is an instrument that uses a combination of two techniques. It's PIXI, or particle-induced X-ray emission, and XRF, which is X-ray fluorescence. So basically what this does is it gives you the elemental abundances of, basically you can go from sodium to bromine on the periodic table. And just by giving you the abundances of these elements, what you can do then is you're backing out the chemistry. And when combining with other tools on board the rover, basically chemistry and mineralogy, really tell a very complete picture of what the conditions were when the rocks were formed and just the various differences between them. So it's been a tremendously successful mission so far. I mean, it's been in operations now since, I think, 2008. It's currently in its third extended mission, so it continues to give us outstanding data. 2,000 rocks have been interrogated, over 3,000 hours of interrogation, so it's done a lot of the heavy lifting. And so this is a view actually from the cameras on board the rover. And to be honest, if you look at it with the right eyes, it doesn't look very different from Earth. I mean, there's a beautiful sedimentary structures that are laid down. And as you know, on Earth, when you go through the vertical stack, basically what you're doing is going through time. And so by interrogating each of these different layers, what we can tell on Mars is what the environment was like all those years ago. So these are roughly 3 to 4 billion-year-old rocks. And so moving from the lower formations up into the clay units that have been detected from orbit, into sulfate units, basically, again, you're going through that, you know, geochronology and the geochemistry evolution of the planet. So it really tells a compelling story of how the environment changed over time on Mars. And without going into a huge amount of detail, that's exactly what we're seeing here, is that there's huge differences in both the chemistry and the mineralogy as you go up, as you're basically climbing Mount Sharp, which was that giant mound inside the crater. And so by looking at these differences, basically what you're able to do is understand different sedimentary environments. And what's really neat is the key results that have come out of this mission is that Mars used to have relatively neutral pH water that persisted for a long time at the surface. And so ultimately, if you've got water around pH 7 that stays at the surface for a long time, that is a very strong indicator that this environment was once habitable. So it was a tremendous success of the mission, and we're super, super proud of everything it's done. Now, the excitement, at least from my part for this week, is Osiris-Rex. So this is a mission where we contributed an instrument called the Osiris-Rex laser altimeter. And so this is a mission that was led by NASA with Canadian contributions of both scientists and an instrument that is an asteroid sample return. So you learn that during the quiz, but basically the goal here is to go out and capture a sample of an asteroid called Bennu and bring it back to Earth to study. Now, the reason this is important is that asteroids, you can think of them almost as the building blocks of planets. These are the materials that started accreting at the beginning of the solar system when it was just dust and gas swirling around and the planets hadn't been made yet. And so as the planets grew and grew and grew, some of the leftover bits just didn't make it into the planets, and they still exist out there as asteroids. So the way I like to think of it is that an asteroid basically is like a time capsule of the solar system. And so if you can go and grab a sample of it, essentially what you've done is you've gone back in time by over 4 billion years to the very beginnings of the solar system to understand what the chemistry of those materials were. And so this can tell you a lot about how planets form, potentially about the building blocks of life and how water was delivered to the early Earth. So really fundamental questions of planetary science. And so after we launched in 2016 on September the 8th, flew for about 2 years to go catch the asteroid, over 2 billion kilometers flown. And when we opened up our eyes, set the cameras on from about 50 kilometers away, this is what we saw, which was beautiful and exciting. And we were all tremendously happy that, we got the spacecraft there. But as you can notice, it is really rocky and really rough, and that was not expected at all. We thought we were going to have a nice smooth surface with lots of fine-grained material, so basically sand covered, with a few large boulders scattered around. And instead what we found was this really rough, really rocky surface with thousands and thousands and thousands of boulders strewn across the surface. And so all of the planning, all of the design, the entire mission had been based around the assumption that we would have an area about 50 meters across that would be completely obstruction-free, so no huge rocks that could damage the spacecraft, no smaller boulders that could, alter the safety or the deliverability, and lots of fine-grained materials that we could suck up. And instead we had this. And so it became very crucial to try to find a location on the surface where we could put the spacecraft down, because immediately we knew that there wasn't anything 50 meters across. So the question was, what was the biggest and how do we do this? So just for context, if you were to put Bennu in downtown Toronto, this is what it would look like. So it's roughly the height of the CN Tower. It's just short. So it's about 492 meters average diameter. I think the CN Tower is like 553 or something. So, roughly 500 meters, but it's translating through space at over 100,000 kilometers an hour. It's rotating once every 4 hours, and it is black. It is dark. It only reflects about 4% of the sunlight that hits it. So you can imagine the challenges we were facing, in the sense that we were trying to chase down a rock, basically a lump of charcoal in black space, flying at 100,000 kilometers an hour, spinning once every 4 hours, and we had to put a spacecraft down safely to try to grab a sample of it. So it was a tremendous, tremendous challenge. But one of the ways that we were able to select a site safely was to use the Canadian instrument that was on board. So this is an instrument called OLA, or the Osiris-Rex Laser Altimeter. And basically you can think of it almost just like a 3D scanner. So again, what's really neat here is we actually took the principles of the laser that we sent to Mars that was shooting up and bouncing off of particles in the atmosphere, but instead we took similar technology, turned it upside down, and then we shot lasers down to the surface of an asteroid. And the physical principle is exactly the same. By measuring the time of flight of a pulse that goes out, bounces off something, and comes back to the detector, basically what you've done is you've measured a distance away from the spacecraft of that specific point. So you can imagine then that as you build up, if you take 10 points or 100 points or 1,000 points at different locations, you start to build up a very detailed 3D model. And what we did with OLA is we actually fired it about 3 billion times. So we covered the entire surface of the asteroid and built a shape model with facets that was 1 point every 7 centimeters. So we understand the topography, the 3D shape of this body, the size of the CN Tower, down to 7 centimeters, which is remarkable, and is in fact the most detailed set of 3D measurements that have ever been made of any planetary surface in the history of space exploration. So it was a tremendous achievement by the team. And this is a very coarse version of what the full shape model looks like. So the warmer colors, the reds and oranges, basically are distances away from the center of Bennu. And the blue colors, the cooler colors, are sort of closer to the center. So basically this is a color representation of the three-dimensional topography of the surface. And what you can see is that there's a bulge at the surface, or at the equator. So it's sort of this, spinning top shaped. And so this was a shape model that was done with only 50 million points. And we now have one, like I said, that's up at around 3 billion points. So it's just remarkable the amount of detail that we were to pull out. So just as an example of one of our high resolution scans, this was a scan that took roughly 5 minutes or so to take, but has over 3 million points just by itself, and covers an area about 100 meters by 100 meters. And so I think the contrast is a little bit high here, but you should be able to pull out a lot of the textures that we're seeing. So down to this sort of individual rock size that we're able to pull out the shape and topography and slope and tilt of the surface. So it's just a tremendously powerful instrument that was critical in choosing a sampling site. Now, in terms of the site itself, so Nightingale was chosen, and what happened earlier this week is that the spacecraft then descended down and tried, that was our original diameter, which was 50 meters. We didn't have that anywhere, so we were actually trying to hit a bullseye. So the flight dynamics team had to figure out a way to get a spacecraft down to something no bigger than the size of a few parking spaces across. And again, you think of the challenge of doing this in the dark, moving 100,000 kilometers an hour and spinning. It's just, it's an absolute marvel of engineering and physics. So what happened is that when the arm was extended, this is an animation, we touched the surface, puffed out a plume of pressurized nitrogen gas that brought up a plume of materials that was caught in the sample head. We backed away, and the plan is to then, in the coming days and weeks, to stow the sample canister inside the Earth return capsule. We'll take some images of it when we do that, close it up. We start the return trip home next March. And then on September the 24th of 2023, and I think it's a Sunday, the spacecraft will be back at Earth, release the capsule, and it will be landing in the Utah desert, where we will go and pick it up and put it into a clean room and triple bag it, where eventually it will be returned to the Johnson Space Center. And so this is hot off the press. This was just released yesterday. This is actual imagery of the contact of the sampling attempt. It's sped up by about 6 times, but you can see obviously the sample head going down, releasing the gas, the plume of particles that came up. And so this was just spectacularly exciting for the entire team. We've been working on it, some people for close to 15 years. And to just see that imagery, I think was very emotional and very exciting for an awful lot of people. And so I think that was a duplicate slide. So I'll skip ahead. The point here is that, so we've learned a lot about the science at the asteroid itself, but really it's these samples that are tremendously exciting for me, because sample return missions are, you can think of them sort of like the gift that keeps on giving. And so, you think about the Apollo samples that were brought back in the 60s and 70s by the US astronauts. We're still making brand new discoveries on those today, because we have a scientific maturity that we didn't used to have. We simply can ask questions that we didn't know how to ask before. And we have new analytical capabilities. I mean, think of the difference in a lab now versus a lab in the 70s. And so when I think about these samples, it's not just, what is the science we're going to be doing in 2023 when they come back to Earth, but what kind of science are we going to be doing on these in like 2050 and 2060? I mean, to me, that's what's really exciting. And so from a Canadian perspective, we contributed the OLA instrument, but in return, we'll actually be receiving a portion of the samples. And so we will be able to make those available to generations of Canadian scientists. And I think that's why I'm so proud to be a part of this mission, is that we're basically enabling the careers of Canadian scientists for generations. Okay, in terms of technology contributions, I'll speed up here a little bit. ExoMars is a program run by the European Space Agency that has 2 different missions. One is an orbiter that is understanding the atmospheric composition and surface features, basically trying to establish habitability and planetary evolution. And so Canada contributed the communications antenna, actually, on the trace gas orbiter, as it's known. The Rosalind Franklin rover, which will be launching in 2022, is also going to have some Canadian hardware, including the rover chassis and wheels. So basically the vehicle itself is Canadian, as are the hazard cameras and the navigation cameras. So you can think about it that, we have the eyes and the feet of the next European rover going to Mars, which is pretty cool. Similarly, from a science side, there's a number of missions where Canadians have been involved. NASA's Mars InSight mission, for example, which is a geophysics lander designed to study the interior of Mars, has a scientist from UBC, Katherine Johnson, who's doing spectacular work with her team. Mars 2020, which is a NASA-led mission that just launched this July, has a scientist from the University of Alberta, Chris Hurd. The ExoMars campaign has multiple scientists on it that are Canadian. Ed Clutis, who many of you probably know, the University of Winnipeg, as well as Livio Tornabinet from the University of Western Ontario. And the Mars Science Laboratory, or MSL, excuse me, that has 3 scientists, Marieke Schmidt from Brock University, John Moores from York University, and Richard Levier from McGill. So we've got this is again just highlighting the fact that there is Canadian expertise coast to coast that is in need of these international missions. And so when they get selected, we at the CSA do our best to be able to support that. And really, this is a great one for us because, when we're talking about, how do we best use our money and how do we use our resources and maximize them, I think this participating scientist program is a really important one in the sense that, it's high impact, get fantastic peer-reviewed publications, lots of media attention, and more importantly, and perhaps even most importantly, they're wonderful training opportunities for early career scientists and students, in the sense that this is a great way of getting the mission experience just to understand what it takes to operate a space program. So it's really exciting from our side, and frankly, one of my favorite reasons for working here. And this is just a plug. I mean, this is the science deck of the Mars InSight lander that, we talked before about metaphorically planting the maple leaf on Mars. Here, we actually did it. So this is the science deck of Mars InSight that includes the Canadian flag on it to represent Katherine Johnson's team. So I think it's, another remarkable example of international collaboration through spaceflight. Okay. Now some fun stuff coming up in terms of where are we going. So I've given you sort of what have we done, but the question is, where do we go from here? And when you think about it, there's sort of a transition from purely robotic exploration into human exploration throughout the solar system. And so a lot of the future work is going to be focused on this combination of not only flying robotic missions for the sake of science, but also collecting data that will help bring people out further and further away from the confines of Earth. So eventually the path that's sort of been agreed to internationally is to Moon as the next step, and then to Mars eventually as sort of the horizon destination for human exploration. And so together there's 16 agencies around the world that have signed a document called the Global Exploration Roadmap that really says this is how we're going to work together, and this is how we're going to get people to the Moon and eventually to Mars. So a lot of our preparatory work, you can understand, is associated with that. And so I'm sure many of you have heard about the Lunar Gateway project, which is sort of the next step beyond the International Space Station. This is going to be a program that will be basically building the next space station, but instead of orbiting Earth, it's going to be orbiting the Moon. And so sort of taking that next toe dip out into the solar system and trying to understand what is it going to take people further and further away from the Earth. And so Canada obviously has a major contribution in the sense that we will be providing Canadarm3. So the next arm that's going on the space station is signature technology for Canada, will be aboard. But as part of the funding that was attributed to this program, there's also something called LEAP, or the Lunar Exploration Accelerator Program. And this was designed specifically for lunar science. And so that's where we come in as planetary scientists. And so we've been very, very fortunate to have received $150 million to be spent over 5 years. And the goal here is really to position Canadian scientists and Canadian industry for that next big step. And so these are sort of initial projects that we're seeding in order to demonstrate our capabilities to take things even further in the future. And so they're supporting a number of initiatives, human health, for example, artificial intelligence and robotics, and also science payloads or instruments. So, there's a broad suite of things that we're doing. And specifically from the planetary side, what's tremendously exciting for us is that we have sufficient funding to fly at least one science payload on a NASA lander or perhaps an orbiter as well. So there will be calls for Canadian instruments to be going to the moon. And similarly, we're very, very excited that we are able to ramp up a micro rover program. So there's going to be a fully built Canadian rover on the surface of the moon that's going to contain both US and Canadian instrument payloads on it. So this is just tremendously exciting times for lunar science here. Similarly for Mars, the strategy is, okay, well, what are the types of data that we're going to need to understand what it takes to get to Mars? And if we eventually want to go there, what missions do we have to start planning for now in order to enable that? So one of them is referred to as Mars sample return. So this has sort of been the holy grail of planetary science for decades, in the sense that bringing samples back from Mars ultimately will allow you to study pristine pieces of these habitable environments in terrestrial labs using terrestrial instrumentation. And so the power of the science questions that we're able to ask will just be, orders of magnitude higher than what we can do with a rover. And so this one actually is going to take 3 flight missions. One, which is a rover to go drive around, pick up the samples you want to collect and bring home. The second is another smaller, more agile rover that would go and pick up the samples that were dropped off by the first one, bring it back to an ascent vehicle or a small rocket that would then be shot into Mars orbit. And then you need a third spacecraft to come and capture that canister and turn around and bring it home to Earth. So it's a tremendous engineering challenge. It's a tremendous economic challenge, and it's always been really difficult to get the program off the ground. But thankfully, it looks like it's happening. So Mars 2020, which was the NASA rover that launched in July, will collect the samples and leave them in a cache. And just last week, in fact, a formal agreement between NASA and ESA was signed in order to complete the flight elements of the other 2 missions. So we're well on our way. And the plan right now is to have samples back on the Earth by 2031. So we're working very hard towards that. Similarly, if we're talking about preparation for humans, what we're going to need to do is identify water resources that they can use. So water is obviously too heavy to carry with you. And if we're going to send people to Mars, they need a source there that's accessible. And so going all the way back to Phoenix, what we've demonstrated is that there are huge reserves of ice very, very close to the surface. And we know this sort of at different point locations, but there's been no systematic way of mapping these near surface resources. And so what we're currently working on a mission concept where a Canadian synthetic aperture radar, or SAR, payload would be put onto an orbiter around Mars to do that very detailed mapping near the surface, sort of the upper 5 to 10 meters you can think of, to identify where's the ice, how much of it is there, and how much regolith is on top of it. So basically, how accessible is it? And so we're working very, very hard right now with a variety of international partners. We are on the verge of signing a letter of intent, at least to form a study team to formalize this with NASA, JAXA, and the Italian Space Agency. So it's really, we're sort of taking the ISS model of multiple agencies working together for a common goal, as opposed to individual agencies simply going out and doing a mission. So I think it's a wonderful model, again, to highlight collaboration internationally. This basically, we don't need to go through this line by line, but it's just highlighting the fact that by doing missions like this, not only are you addressing critical human questions, but you're still collecting science data, right? And so these science data are able to address some of those questions we still have outstanding about Mars. And so understanding the geological and environmental history, potential habitability, these are fundamental science questions that these data are going to be able to address. And so by flying 2 missions like this, it's tremendously exciting for us to be able to contribute both to the human exploration side and to pure science. So bottom line, if you remember nothing else from this last half hour of your life or so, please take away these 3 points. The first is that, typo here. So Canada continues to be a partner of choice for international exploration missions in general, not just Mars. Basically, we're known as a reliable partner, and so agencies will come to us to help, and we've answered the call every time we were able. And so even small investments from Canada with the budgets that we have still do leverage billions of dollars of investment internationally. And so we're doing our best to create those partnerships and to keep them in order to make those really, really effective Canadian contributions as well. And specifically for Mars and the Moon, you know, we have an opportunity here to make some really historic achievements in the coming decade, like legitimately the next few years. So the first Canadian vehicle on the surface of the Moon, potentially contributing to bringing samples back from Mars and identifying water ice resources for eventual human exploration in the 30s. You know, we're at a very, very exciting time right now for planetary science. And so I'm just really, really excited and proud to be part of it. And yeah, I mean, I've been a space nerd since I was a little kid, and the fact that I get to do this for real now, I sometimes can't believe it. You know, I'm excited to be part of it, and thank you for listening, and hopefully there's still a bit of time for questions if there are any. Thanks so much.
Thanks so much, Tim. There's so much exciting stuff going on right now that it's great to hear. So we do have some time built in here for a break for all of our people who have been with us all morning or afternoon or whatever time of day. So we will take some questions from the audience if anybody has some questions. And Tim's colleague Caroline is here as well to answer questions about more detailed geology. So we would welcome anyone with questions.
Yeah, feel free to also unmute yourself and ask the question yourself. I know we have some comments during the presentation that said, fantastic, this is amazing. That is so true that we are able to ask new questions to the same material.
Yeah, and I think that truly is the power of sample return missions. I mean, you know, effectively what you do when you bring back a sample from, you know, if it's the Moon or an asteroid or Mars, ultimately, essentially what you've done is you have turned your science team into everyone that is living now and everyone that will be living in the next 100 years. And so, you know, just the number of people that can work on these orders of magnitude. Similarly, the power of the tools that you can use. I mean, there's some instruments that flat out you will never be able to fly into space. I mean, how do you fly a synchrotron into space? How do you take a, you know, a room-sized electron microscope and fly it? You can't. And so by bringing the planets to us, essentially what you've done is not only have you turned your science team into everyone that is currently living and everyone that will be living, but what you've also done is you've turned your spacecraft into every analytical facility on Earth. And so the power of the science you can do when you bring the material back is just light years ahead of what you can do with flight programs.
I was wondering if Caroline wanted to tell us a little bit about her experience working on the Apollo samples.
Yeah.
Yeah, I can. But before I do, I just wanted to mention that we're currently working on the plan to create the Canadian portion of the Canadian samples. And just for you, for context, we'll become the fourth nation to actually create samples from out of space. US and Russia has some, and Japan has really, really small particulate for their mission that was sample return, but didn't function completely, but they're preparing to receive more samples from another mission, and Canada is doing that right now. So I just wanted to let you know that. And yeah, so I had a chance to work on the lunar samples. That's already 10 years ago or 9 years ago. So time goes by. In order to have access to the samples, you need to fill in a proposal. Any scientist in the world can fill in a proposal, send it out to NASA, and then there's a committee that assess whether they would want you to do those analysis or not. So you need to have your analytical plan. You can have selected your samples up to a certain point, although once they've agreed that you could do your study, they will help you to select the samples with you to make sure you have access to really the right samples you want to do your study. And then once everything is sorted, there's a loan agreement that needs to be signed. And the responsibility for this, the sample goes with that loan agreement. And basically you carry the samples with you at all time unless they are locked in a safe with a specific locker. And so I bought a purse at that time where I had a box where I had special little boxes that they were 10 sections. So the boxes were made with membrane so that the 10 section couldn't move and was protected in case of a shock. And basically when the samples were not at the cabinet, because I was doing my work at CSA, but I was analyzing them mostly in Ottawa and in Quebec City for the microprobe and for the laser ablation that was in Ottawa. So I was carrying them around and basically they were with me at all times. So that was interesting. But it's how precious they are. I mean, it's, you know, we don't have a chance. It's not like you drop it, okay, let's go pick another one. It's not working that way. So that's how precious they are. And I found really nice discoveries in those samples. So they are the ilmenite first in the basalts are enormous crystal, as on Earth they are little needles, and there's not much of ilmenite in the terrestrial basalt, and the maximum titanium content you can have in the terrestrial basalt maybe is the 3%, but on the moon you can go up to 17%, and that resolve in basalt bearing maybe 20 to 25% of ilmenite, and they form these really large crystals. And there's an interesting story in those crystals that the major element fractionation compared to the trace elements don't work. And the story there is that the trace elements are so much higher in concentrations than we have in certain terrestrial basalt, then they start behaving more like a major element than a trace element. So there's stories like that about the discoveries. Anything you will analyze, you will make new discoveries. So I'm not sure what the time is like. Maybe I can stop to see if there's questions.
We do have.
We talk for 2 days.
Yeah, we could talk about rocks all day long.
Exactly.
We do have a question from Arturo Valencia talking about are there Canadian people asking to use their taxes on different purposes rather than space exploration? Canadians should be proud of their space agency, but I wonder if there's another view to it. So I don't know if you or Tim want to discuss about
Sure.
funding to the space agency. That is a tough question. I know, speaking to all of us who are absolutely in love with space and scientific research, it's easy to say absolutely this is a very high priority, but that's not everybody's opinion.
No, definitely, and it is a fair question because I think for a lot of people there are more immediate needs with more tangible outcomes, let's say, and so there are some cases certainly where space investments in space infrastructure is absolutely critical. I mean, we wouldn't be talking right now by video over screens if it wasn't for space technologies. You wouldn't be using your phone if it wasn't for space technology. You couldn't have driven, your GPS. Think about, without space technology. So there are fundamental elements of space technology that affect you every single day of your life. So that portion, I think of it is very clear cut. The exploration side is a little bit different because, there is the argument of, why would we send a rover to Mars when you can put it into a hospital on Earth? And I think in a lot of ways it's a fair question, but when you think about space exploration, it does a number of things in a number of different ways. So if you talk about, just from an inspiration standpoint, obviously we're all sort of preaching to the converted, but if the numbers are there to support that, interest in social media, in regular media, increases drastically with wonderful pictures coming back from space astronomy with Mars landings. And so there is an inherent, public engagement element to it. There's the training elements. These are wonderful platforms to train students and early career scientists in terms of whether or not they stay in the space industry or not. you become a better scientist when you work on space missions. And so training that next generation of highly qualified people for the Canadian economy and Canadian jobs is critical. There's the investments themselves that create jobs. If you look at the money that's spent to build OLA or to build an APXS, this isn't money that you put in a rocket and launch to Mars. This is money that's being spent in Canada. It's creating jobs in Canada. It's creating highly qualified jobs in Canada. And really, the numbers are there actually that for every dollar invested in space exploration, there's actually a multiplier effect on the economy in general. And so when you think about it, it's not just a question of spending money to send a rocket to Mars. What you're doing is you're investing directly in the Canadian economy and in the Canadian people. And so I think there's a lot of different ways, whether it's just excitement or training, or even the economic argument, space exploration is beneficial to Canada in a wide variety of ways.
Amazing. Thanks, Tim. Does anybody else have any final questions before we finish up this section? Georgie Statsi gave a question. Thanks a lot for the great presentation. How difficult is it for a geologist coming from the mining industry to enter in the space sector?
Do you want me to take that one? So that's basically my path. I've studied on anorthosite and iron titanium deposits, and then was lucky enough to have a postdoc position at the Canadian Space Agency, applying terrestrial knowledge to space. And although I think it's not the typical path, I think it's worth pursuing, because to me, there's not enough exchange between terrestrial and planetary. And I always remember, to me, we say planetary science, and I'm like, what's the first planet that we study is the Earth. So it's kind of, you have Earth science and planetary science, but really, these should be like this, right? So I don't think there's a magical answer that you have to say this is the path if you want to go from there to there. But my answer is, if you want to make that jump, look for any opportunity. There are profs that do both. I think one easy path is to do advanced studies and postdoc. I think that might be an easy path to go. And other than that, you look for any opportunity and you jump on it. And there are many opportunities to participate into space adventures. So.
If I could just build on that, I think Caro is an excellent example. You hit the critical ones, like Earth is a planet too. And traditionally what we've seen actually is that expertise in traditional terrestrial geoscience is tremendously applicable to planetary exploration. And in fact, a lot of the best scientists started as just terrestrial focused scientists, because they're not sort of polluted by the magic of space. It's just, mineralogy is mineralogy, geochemistry is geochemistry. And if you understand the physical processes behind the data, then you are much better qualified to do that, whether it's on Earth or on Mars or on the moon. So I started, I was a terrestrial geomorphologist. I was just doing permafrost work in the Canadian North, and then learned that there was a link between permafrost geomorphology and ice on Mars. And so I think there's a number of examples where you can take that terrestrial geoscience knowledge and apply it to a planetary problem. And again, physics is physics, chemistry is chemistry, it works. And so if you understand it here, you can apply those principles anywhere.
Awesome. That looks like all the questions that we've had so far. I really want to thank Caroline and Tim for spending some time with us this morning, and we're very much looking forward to hearing what else the research that's coming out of the CSA. There's definitely some very exciting stuff coming up with the asteroid, and so much more to learn about the moon and Mars and any other planets and planetary bodies that we're involved in. I welcome both of you to stick around for the next session. We're going to be doing breakout rooms. If you're interested in meeting some of the participants today in our session, you're welcome to stay. I also understand there's lots of exciting science to get back to, so thank you very much.
Yeah,
And
I'm afraid I'm going to have to step away, but thank you though.
Thank you so much.
Yeah, me too, unfortunately, but don't hesitate to keep in touch if anything. It was a pleasure to be here this morning.
Yes, Kristen knows how to get in touch with us.
Yeah.
So no, if there's ever any follow-ups or any questions, please never hesitate. We're happy to help out however we can.
Yes, for sure. We definitely, hopefully, be in touch in the future.
Excellent.
Excellent. Hopefully you can see my screen there. I just want to invite everybody, since we've been here for quite a while after all that exciting thing, if you have a chance to stand up and kind of stretch, and hopefully all of our participants have had a little bit of a break. Our next session, I think we're going to jump right into it. We had a 15-minute break set in the schedule, but I think we're going to just keep pressing on so that we have a chance to meet our next panelists. So we have 3 people that are going to be joining us for the next session. We have Zaid, Katie, and Sao Chen, and they're going to tell us a little bit about different organizations that they're involved in. And these are absolutely fabulous organizations to become involved in students in a mentorship capacity. Zaid is the national point of contact for the Space Generation Advisory Council. Katie Harris is the Director at Large for SEDS-Canada, which stands for the Students for the Exploration and Development of Space. And Xiao Chen joins us as a Canadian alumni to the International Space University. What I'm going to do now, if you haven't had a chance to experience breakout rooms in Zoom, I have randomly assigned everybody in the meeting to each of one of these 3 breakout rooms, which will have one of these representatives in it, and we will have 15 minutes with each panelist to allow you to hear a little bit about their organization. And when the 15 minutes is up, I'll give a 2-minute warning to wrap up any discussions that are happening. I will move the speakers to the next breakout room. And so if there's any questions, don't hesitate to come back to the main room and let me know. This portion will not be recorded because in the breakout rooms we won't be recording. So feel free to turn on your videos to share that, and let's give this a try. So Zaid and Katie and Xiao Chen, thank you very much for joining us and welcome. While we're in the main room, I don't know if you want to just give a quick introduction of yourself, just a quick couple minutes about yourself so everybody kind of sees the same thing. And of course, when you're in the breakout rooms, you'll have a chance to go more in depth with your organization. So Zaid, do you want to start us off?
Yeah, for sure. So hi, everyone. Pretty incredible to be part of this virtual field trip. So as Kristen mentioned, I'm the national point of contact with the SGAC, and I'll dive into a bit of what we do. It's an international non-governmental organization, and there was a question earlier about how to get involved from a non-traditional field into space. So that's the kind of question that I'm very excited to talk about, and it's something that SGAC is really well set up to connect in terms of academic and professional developments. My personal background is I've been involved in a variety of space missions designs across the European Space Agency and at the Canadian Space Agency. So I've really had a great set of opportunities to expand my breadth of topics. I've covered things like space operations to in situ resource utilization on the moon, and all the way to Earth observation missions. So that's more or less what I am up to these days, and pretty excited for our breakout sessions.
Thanks so much, Zaid. Katie, do you want to go ahead and introduce yourself?
Sure. So my name is Katie Harris. I'm a second-year medical student at the Memorial University of Newfoundland, and I'm also Director at Large for SEDS-Canada. So once you pop into my breakout room, I'll tell you a little bit more about SEDS-Canada and how you can get involved and how we advocate for space and student interest in space in Canada. And then if we have leftover time, I'd love to talk to people about what kind of paths they're interested in taking. I started in astronomy and ended up in space medicine. So I think that there's lots of really cool areas of space to get into.
Thank you so much, Katie. And Xiaochen, would you like to introduce yourself?
Yes, hi. So my name is Xiao Chen, and as Kristen introduced, I am a graduate from the International Space University. So today I would like to talk about my experience at ISU and how this how studying there has led me to where I am right now. I am currently a master candidate at Western University or University of Western Ontario, and I study planetary science. I believe a lot of people here are interested in planetary science, so I want to kind of introduce how ISU has affected my decision to kind of choosing a different career than what I've been previously doing. So you're all welcome to join me.
And thanks so much for sharing that. So I will go ahead and start the breakout rooms. If you haven't been in a breakout room before, it may seem a little bit like you are